this thing called the rank. Well, we just calculated the dimension of that subspace, which was 3. Well, the dimension of the row space is called the row rank. And in a minute we're going to talk about column rank, so I'll just go ahead and write that too. The dimension of the column space is called column rank. Okay, so now let's do the same problem, but let's find a basis that actually consists of vectors from the original set. This time, we take those vectors that we had, the v1, v2, v3, v4, and instead of writing them as rows, we're going to write them as columns, and we're going to solve the associated homogeneous system for that. Now notice in the last one, we just wrote them as rows, and we converted that matrix to reduced row echelon form. Now we're going to write those as columns, and we're going to augment it. We're going to actually solve the associated system. So it turns out to be the following. Make sure. 1 minus 2, 0, 3, negative 4. Yes. So when I write v1, v2, v3, v4 as columns this time instead of rows, it looks like this. 1, minus 2, 0, 3, negative 4, 3, 2, 8, 1, 4, 2, 3, 7, 2, 3, minus 1, 2, 0, 4, 3, and the augmented system. Now we've done this before actually. If you remember a couple of lessons back when we were looking for the basis of a particular subspace, this is what we did. We solved the associated homogeneous system. And then when we converted it to reduced row echelon, which we'll do in a minute, the columns that have columns that have leading entries, the corresponding vectors are a basis from the original set. So let's go ahead and do that. We convert to reduced row echelon, and we get the following: 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 11/24, 0, minus 49/24, and 0, 7/3, 0, 0, 0, 0, 0. Okay, here we go. Now we have this column, and this column. The first, second, and third columns have leading entries in them. Because they have leading entries in them, the original vectors corresponding to them, in other words, that vector, and that vector, which are part of the original set, they form a basis for the span of that original set of 4 vectors, right? We had 4 vectors. Well, we don't need 4 vectors. We need just 3. And that's what this procedure does. It allows us to find a basis consisting of vectors from the original set, whereas the thing we did before allowed us to find a basis that had nothing to do with the set. And notice we have 3 of them. It's not a coincidence. So, in this particular case, we could take v1, v2, v3, the original, that is a basis for the span of S. In other words, the span of S, which is the row space. Row space, because originally we wrote them as rows, row vectors. Here we wrote them as columns in order to solve it in a certain way so that we end up with vectors from the original set. It's still the row space, or the span of S, if you will. Okay. And again, the row rank, well, the row rank is the number of linearly independent vectors in the basis, or the number of vectors in the basis. They are linearly independent by definition of basis. It's 3.